Welcome to this explainer, presented by Dr. Christophe DeLong and Connexa Formation. Today, we're diving into a super fascinating intersection of biology, engineering, and philosophy. We're looking at a direct comparison between one of the absolute most complex structures in nature, the human hand, and the bleeding edge of robotics. Specifically, we're talking about Tesla's Optimus Gen 3 humanoid robot. So, how close are we to actually replicating human movement? Well, to answer that, we've got to start with a really simple engineering claim.
Tesla proudly announces that the Optimus Gen 3 hand has exactly 22 degrees of freedom. Now, in robotics, a degree of freedom is basically just an independent direction of movement that a joint can make. And hitting 22, that is a massive, massive technical achievement for a humanoid hand.
But the human hand, by comparison, has 27 degrees of freedom spread out across 29 joints. When you put those two numbers side by side, 22 versus 27, it paints a very specific picture of exactly where the technology currently stands.
Looking at this initial engineering claim, honestly, the gap seems incredibly small. It kind of looks like just a minor hurdle, right? Like a residual engineering problem that the very next generation of robots is just going to easily close. I mean, just add 5 more degrees of freedom, and boom, we're there. Well, that's definitely one way of looking at it. But according to the source material we're looking at today, that is precisely where the whole problem begins.
Because relying purely on degrees of freedom hides a really fundamental architectural difference between biology and machinery. You see, degrees of freedom only describe joint geometry. They just tell us how many independent directions of movement are available. But they tell us absolutely nothing about how those movements are actually coordinated, how sensitively they're guided, or the overall architecture that they fit into.
La vraie nature de la main, or the true nature of the human hand.
We really have to remember that the hand isn't just a flat mechanical pincer. It is a dynamic 3D structure and an absolute sensory powerhouse. Your hand is literally packed with up to 2,500 mechanoreceptors per square centimeter, especially right there in your fingertips. And these are just generic sensors either. They're divided into 4 distinct types. You've got Meissner corpuscles for light touch and texture. You've got the deeper Pacini corpuscles for high-frequency vibrations, like if you're holding a trembling tool, Merkle discs for sustained static pressure, so you can feel an object's shape without even looking at it, and Ruffini corpuscles that code skin stretch. All of this creates a real-time tactile motor feedback loop with just extraordinary resolution. So the crucial point is captured perfectly right here. Amputating its sensory dimension to focus on its motor degrees of freedom is to miss half of what it is. The hand is just as much a sensory organ as it is a motor one. You simply cannot separate the two in biology. Estimating weight, detecting a microscopic slip, and adjusting your grip strength in milliseconds, that is all sensory-driven. To reduce the hand strictly to its motor degrees of freedom completely misses half of its fundamental identity. Part 2, L'Exploit Technique d'Optimus, the technical feat of Optimus. Because look, we absolutely must objectively acknowledge the immense and serious technical progress Tesla has made here. Their design brilliantly illustrates smart structural biomimicry. In humans, to avoid having super bulky fingers, our hands actually rely on extrinsic muscles located way up in the forearm, pulling on tendons like cables. Tesla studied this and did the exact same thing. They moved the heavy actuators into the forearm and used cables to pull the fingers. It is really structurally sound biomimicry. However, Optimus still relies on force sensors rather than a rich array of varied mechanoreceptors, and it uses a mechanically flatter, more symmetric grip rather than those dynamic 3D biological arches we talked about.
This brings us to part 3, 5 prismes d'analyse, 5 frameworks of analysis.
Comparing these hands really forces us to choose a framework, and each lens reveals completely different truths. Our first framework is pixels. Think of this as the language of motion capture. It describes movement as pure 3D trajectories, kinematic data points plotted over time. This framework is highly objective and super measurable. If you overlay the motion of an Optimus hand turning a key with a human hand doing the exact same thing, the trajectories might perfectly align. This is the lens where Optimus looks the absolute most human-like. But wait, this raises a really major question. Just because a robot's hand traces the exact same path as a human's, does it mean the movement is actually generated the same way? The Pixels framework does a great job describing what is happening, but it completely fails to explain why or how it's happening. 2 identical paths can actually be produced by entirely different underlying mechanisms.
And that brings us to our second framework, vectors.
This is basically classical Newtonian biomechanics. It focuses on mechanical forces, joint moments, and muscular torques. It's a highly useful framework for engineering a robot like Optimus because, you can perfectly measure the electrical actuators and calculate the exact mechanical force. But it completely misses the quality of coordination. You can have the right forces, but still have a completely rigid and energetically costly movement. Vectors just don't capture biological intent.
Now things get a little deeper with our third framework, diagonals. This framework, which is rooted in rehabilitation methods, shows that natural human movement doesn't actually happen in pure isolated axes. We don't just flex or just abduct. Movement occurs in combined 3D diagonal patterns that are driven by neuromuscular synergies. Our brains don't independently control 27 separate degrees of freedom. Instead, the brain activates a few powerful synergies that smoothly coordinate multiple joints all at once.
So, looking at robotics through this diagonal lens, we have to ask, is Optimus coordinating its grip fluidly through combined synergies? Or is it rigid because it's being forced to optimize one isolated mechanical axis at a time? This underlying difference literally dictates how fluidly a robot can adapt to a totally new, unseen object. Then, there is the spirals framework. This highlights the fact that human anatomy naturally forces helical movements. Because of exactly how our joint surfaces and fascial tissues are shaped, biological movement is inherently a spiral. Think about it. When you make a fist, your wrist automatically rotates slightly into pronation. When your biceps flex your elbow, they naturally twist your forearm. These aren't deliberate motor commands you're thinking about. They're automatic, emergent properties of biology that are completely absent in purely separated mechanical joints.
Finally, we look through our fifth framework, chains. This views the human body not as a collection of isolated, independent parts, but as a continuous tensgretary system connected by an entire fascial network. A tension in one single area mechanically influences the entire system.
Just think about how this builds biologically. Tension from the plantar fascia at the very bottom of your foot physically connects through your hamstrings, up through your thoracolumbar fascia and your back, down the posterior chain of your arm, and all the way to your fingers. It's wild, but the strength and quality of your hand's grip are actually determined by the postural organization of your entire body. Now, because Optimus lacks this continuous fascial tension connection, its hand is really just a disconnected terminal effector. It can optimize its grip entirely independently of where its robotic feet or spine happen to be. But the human hand? It's the terminus of an entire bodily system. The quality of the whole chain dictates the quality of the hand's movement.
Par 4, au-delà des degrés de liberté, beyond degrees of freedom.
Ultimately, analyzing movement through just one single lens severely limits our understanding of what movement actually is. All 5 of these frameworks don't contradict each other, they complete each other. The source material summarizes this perfectly. The human hand cannot be reduced to its degrees of freedom any more than a symphony can be reduced to the list of notes that compose it. The hand is a complex, interacting symphony happening across all 5 of those frameworks simultaneously.
The true comparison only begins when we decide how we're going to look at the problem. As we continue to build these incredible mechanical reflections of ourselves in metal and code, I want to leave you with this to ponder. When we evaluate success in humanoids, what essential parts of our complex, biological humanity are we choosing to measure? And by relying on just the numbers, what are we leaving behind? Thanks for exploring this with me, and keep questioning the frameworks you use to see the world.